Welcome to another session of the Industrial Engineering and Operations Research Seminar here at our Universidad of Ibáñez. This time, we're delighted to have Professor Rockafellar invited as an invited speaker, and the introduction will be done by Professor Pagnoncelli. Okay, thank you.
This would mean to choose the pair, the decision vector x and the level b, such that this inequality is satisfied, and try to do it with the lowest b that we can do for this. But it still comes down to this kind of inequality and its interpretation as a level of risk that we allow certain exceptions, maybe. But to choose this risk measure is expression of preferences. There's no single way, no textbooks, you should always use this, always use that. It's going to come down to the situation and what you want from it. So here's some examples. So remember the notation here. We have a random variable that depends on x, and we convert it to a numerical function by the choice of risk measure. We're going to go through here four very typical things, a long tradition in engineering and operations research. First of all is the worst case analysis, as in typical game theory. So I'm using here the expression the supremum to mean the top of the range of the random variable, the essential supremum technically, the highest that you could reach. And so I look at a random variable and I assign it to it this highest value that it could have. Could be infinity. I allow infinity. It would have certain meaning depending on the situation. And then to say that I have this adequately, it's adequately less than or this is the numerical function, would mean that the random variable is less than or equal to that bound almost surely with probability 1. And this is a very typical way for people to do things. But suppose you're building this bridge again. Can you build it so that there is absolutely no hurricane, earthquake, or flood that could destroy it? It's probably impossible. That's why in engineering they build things for 10-year floods, 100-year floods, 1,000-year floods. This is some attempt. And I'll get to that scale. That's a different concept, a probabilistic scale. Anyway, that's very traditional. Another idea would just be to replace a thing by an expected value. And that happens a lot, especially in the objectives. People use expected values there. I use double notation. I like the mu for mean value and I like the e for expectation. They're both good. And then to say that we have this constraint, this condition is satisfied for the numerical function, that's the concept of adequately here, would mean that the random variable is less than or equal to this value on the average. So if you are thinking of minimizing the expected value, then according to what I'm explaining, you're thinking of finding the lowest b such that on average you would be less than or equal to that b. But if you're very worried about cost overruns, maybe you'd be worried about the worst cost or something like that. So expectation isn't the only way. All right, now a third version is to, but this isn't very good. Only on average the bridge won't collapse. That's not, in many cases that wouldn't be adequate, right? So, but then you could put in, try this, you have a safety margin. So instead of just having a mean, you had some multiple of standard deviation. This is very similar to a confidence level in statistics. Say lambda equal to 2 standard deviations, and then so you take the random variable, you apply that. That's taking the random the risk measure to be the mean plus a multiple of the standard deviation. Then to say that this is less than or equal to b, it would mean that this your random outcome satisfies this inequality, except in the tail that's over so many standard deviation units. So this sounds very good, and it's used a lot in reliability engineering, for example, but it has a fundamental mathematical flaw. There's something wrong with it, which I'll explain in a moment. Now, still the fourth one, which is very common, is a probabilistic approach, which depends on quantiles. So you take a probability level 95%, let's say, and you look at the 95th quantile. This is the level 5% or above, the outcomes are above this, 95% below. It's a little difficult with what happens exactly at it, but we won't get into those technicalities. So you take a random variable and you look at the 95th quantile, and that gives you a number, a value. And then to say that this 95th quantile is less or equal to b would mean that the probability of the constraint being satisfied is 95%. Very common, probabilistic constraints. Now what's wrong with these? What's wrong with this is a lot of bad behavior of this quantity, discontinuities, and other kinds of things, which we'll see in a minute. Now to remind you with a picture here, if you have a random variable, you can introduce the conditional distribution function. And I'm drawing it as if it's continuous, but it might have flat spots, it might have jumps. This all has to be handled in a more technical way, but it's very easy to do. You take this 95% point on that interval from 0 to 1, you go over, you drop down, and that's where you get the 95th quantile in the distribution. And in finance, this is called the value at risk. And it can be identified vaguely as the inverse of this function, but the trouble is that it has level spots and jumps. Inverse needs to be treated in a little more subtle manner. Now, there's a concept that Stan Grasov and I introduced, or at least well, there were some ideas floating around about it, but we're the ones who put it together with some important formulas that I'll discuss in a minute, called the conditional value at risk. And in this picture, it has several interpretations, one of them corresponding to that area above the curve. And so we're also using the word super quantile as a sort of application free name. And so we don't want everybody, say, in engineering, to have to use finance terms to discuss this concept. So one way to describe it is that it's the average value in that upper interval above the p quantile. But there's a little technical problem if there's an atom of probability right at that, but it's easily solved. But another formula for it is it's the average of the quantiles above that level, and that corresponds to the red area at the top. And so here would be another measure of risk. And this measure of risk has much better properties than the others that I put down there. And I'll get to that in a second. So one of the things you could do is take the measure of risk to be this super quantile at 95% instead of the quantile. And then to have the thing be adequately less than or equal to b would mean that the random variable was less than or equal that level, even on the average in the remaining part of the distribution. So it's a more conservative but much more stable and better mathematical concept to work with. So now you wouldn't want to just take everything as a measure of risk. These are the axioms that you ought to have for a measure of risk, and that people have studied and managed to put together a beautiful theory from. So I'm thinking of my random variables in the sense of functions on a probability space, and I'm going to take them to have finite mean and variance. You can do it in many ways, but I think this is good and at any end is more convenient. Now, one of the things you should have is if your random variable as a special case is not really random, it's just a constant special case of the random variable, then the risk that you give to it should be that constant. You shouldn't distort that constant. If you're sure to use $1 million with probability 1, then you should call the risk level as minus 1 million. Another is convexity. I'll explain that a little more, perhaps a little later. And then lower semi-continuity, this is just a concept that if you look at all the random variables which are below a certain level of risk, then that should be a closed set with respect to convergence of mean and variance. And this is my picture. Now, some properties besides these basic ones that would be interesting would be, and have been studied a lot, is positive homogeneity, that if you rescale the random variable by a positive lambda, then that lambda should rescale the risk in the same way. Maybe you want that, maybe you don't. That's why this is supplementary. Another one, which seems that one would want it, is that if there are two random variables, and no matter what happens, with probability 1, the outcome of x is less than or equal to cost outcome of x prime, then the risk with x should be less than or equal. It seems obvious one would want that. Another is aversity. If there's risk in something, then you shouldn't be satisfied with just the average. There's some premium to be paid for the risk. Now, some of these have been studied under the name of coherent measure of risk. It's introduced in finance for banking regulations, and that includes these first three, along with this, well, I have here monotonicity. Actually, they also put positive homogeneity in, but you could drop that and still call this a coherent measure of risk. Another idea is this adverse measure of risk, which instead takes these first three and adds this. And we actually want all the properties. I'll explain something about why it's divided up in this way. And so the coherent measures of risk were introduced in 2000, and they have played quite a big role. So, for example, the people who introduced this said that you should have this convexity and positive homogeneity because it has to do with hedging in a banking situation. Like, imagine that you have a portfolio of stocks and bonds or risky, some things like that. Let's think of them, though, not in terms of paying, but in terms of losses, because we want to have this cost orientation. One portfolio in terms of losses, and there's a regulation that says if this is your random variable of losses, this is the amount of cash you should keep to be safe about it. Okay, have another one, different losses, and this is the amount of money you should have to keep safe for that risk. then it should be true that if you combine the two, then the sum of the cash should be safe for both. This is actually the origin of the convexity axiom. This is where convexity comes into this. All right, now, but we'll see, though, that some things are not coherent. The value at risk is not coherent, and this is how this all originated in finance. But from a mathematical point of view, in my background, one of the things I like about all this is if you have a coherent random variable, and then you create this numerical function, then you have something that preserves convexity. You don't destroy it. Another thing is you can create dual things in many ways. Now here are these typical examples. So we look at value at risk, which is the quantile or the probabilistic constraint. And the trouble is that fails a number of these things. It fails convexity. It fails lower semi-continuity. And it fails aversity. Now, if you took the super quantile or the C-var, it satisfies all of those axioms. Now, if you also took the essential supremum, it would satisfy all the axioms, but maybe it's not suitable. You don't have a budget that can build a bridge which cannot possibly fail under any circumstances. Now, here's the one that was interesting. The one that added to the, well, okay, this is just the expectation. That satisfies all the axioms, but it's maybe too feeble, and it's not averse. That one it doesn't satisfy. Well, what about this one with a safety margin? That actually lacks monotonicity. You could have one random variable that the cost will, no matter what, the cost of x will never be more than the cost of x prime. But if you use this measure of risk, it could say that the risk is reversed between them. So it's incoherent. Right? Other various operations you can use to form things. So let's just skip over this. Here's another idea, which is quite important and relates to robust optimization. And in robust optimization, a very popular approach, it's basically a worst case approach. But in a worst case approach, you're supposed to, you first of all have to identify the probabilistic setting because some things are so unlikely that you don't necessarily want to include them, because in robust optimization, everything is treated more likely, and you could just, as a matter of modeling, assign importance or likelihood of some sort to those different levels of uncertainty, positive numbers that add up to 1. And then if you do a worst case over each of these separate regions, the worst of these, omega is your set of future states. The worst future state in each region, that, and then you weight that with these weights, then you would again get a measure of risk that's coherent and pretty good. And there's another alternative interpretation to that, is that it has to do with information. The decision maker is only won't know what the future state is, will only have certain information, observations, which will lead to equivalence sets. That is, the decision maker cannot distinguish at the time of the decision the different states in here. Knows the probability of a state being in here, but does not know which future state in this region actually will occur. And in that case, you could be led to the same thing. So it would be a sort of an interpolation of robust optimization, and for some reason nobody really seems to pick up on and study. Now, for value at risk and conditional value at risk, the discovery that Joseph and I made, which propelled a lot of the subject, was a single formula, which in fact came out of the theory of conjugate convex functions and convex analysis. But it's not obvious in the papers that we initially published how that was true or why that happened. So this is convex analysis in action. But from this, there's a single formula where we have a one-dimensional optimization problem. We're going to choose a probability level between 0 and 1. And then you think of a minimization of this quantity where you take the expectation of the excess. This max is with the 0, this is the excess of x above the level c. You take the expected value of that, you rescale it, you add this c out here again, you minimize over c, and the minimum value will be the conditional value at risk. And the c that you get will be the value at risk, at least if it's unique, otherwise technically it should be the lowest. And this formula can be brought into action because if, for example, you had an optimization problem where you were minimizing a conditional value at risk at level P0 of a C0 random variable, subject to different levels of something about some other random variable, you could put in this formula and reduce it. It seems like the formula, the concept of conditional value at risk is too complicated to work with, but this solves it. Then you can reduce such a formula with a max. You can, and there are more things you can do, tricks that are well known in optimization. And if, for example, you had a sort of a linear situation, as often occurs in finance, you can convert this kind of optimization to linear programming. Now, I'd like to say something more about reliable design. A lot of engineering design, and this can happen in systems in operations research too. You're designing a healthcare system which shouldn't fail. So the way engineers approach this is they have, you remember our basic picture here, we have of course I have 2 dimensions in my picture here. I have a cost expression that depends on my decision variables, but also on some other parameters which could become random variables. So I'm looking here where I had 2 coefficients or parameters, V1 and V2, but since they became random variables, it meant I have a probability distribution in this V1, V2 plane. And now the C is some function on this V1, V2 plane, but it's a function that depends on my decision, little x. But anyway, if we look at a random variable here, capital X, the idea is that you have a failure if this random variable is positive, it comes up. Those are the failures, and we want to know the probability of failure. Okay, so you take the region where that expression would be positive, and you take its probability. That's the probability of failure. So various ways to write it down here. But remember that this thing depends on your decision. If I change a decision, I'm changing the function there. So probability of failure, that line would move around. And so a lot of engineering is based on a probability of failure should be less than or equal a certain amount. It's written into many government regulations. The probability of failure cannot be above a certain amount, but maybe bureaucrats think you can work with that. From a mathematical point of view, it's very hard to deal with that. How will you deal with the probability of failure, especially with small probabilities? Because you're going to deal probably with some historic data. So how can you compute it or estimate it? But also, as I say, the trouble is that it will depend on your decision. So it's not, there's a lot of, I see a lot of difficulty in things that are using statistical methods in optimization, in that methods are designed to compute one quantity. But in optimization, you want that quantity as a function of your decision value. And so you have to have a parametric approach, and that's hard to achieve. Anyway, one idea is that you could, and then as I said, there are all kinds of discontinuities because this probability, depending on the quantile, is a bad idea. But you could instead use this, what we're calling a buffered probability of failure. I've been working with that, especially with a different collaborator, Andreas Roystedt. Anyway, this is a better concept, and it somehow creates a buffer. So I'll go on from that to something else. I want to mention another part of this is that something called a measure of deviation, and this is what is going to assess the uncertainty in a random variable. And it's supposed to be a generalization of standard deviation. Now, one of the criticisms of standard deviation, which people use a lot, is it's symmetrical. So a deviation that gives you something worse is treated the same as a deviation that gives you something better. There's something a little illogical about that. So a measure of deviation, you could say, is if you had a constant random variable, there's no uncertainty, so deviation should be 0. If it's not constant, it should be something positive. Not necessarily symmetric, though. If I apply to not minus x, I might get a different number. Convex, lower semi-continuity. There's some upper homogeneity. And here's a very strange axiom, that the deviation should be never more than the upper range of a random variable as going from its average up to its highest value. We'll see where this comes in a moment. Turns out, this is another thing I did with Horacio in Florida, is developed that it's actually very easy. There's a one, but nobody thinks about it this way. They kind of mix all the concepts together. There's a one-to-one correspondence between deviation measures and risk measures if you're thinking about these risk measures and the averse risk measures and these deviation measures. And it's simply like this. If you have a deviation measure, could be, for example, standard deviation, it could be 3 times standard deviation, it could be something not symmetric, add it to the expected value, call that a measure of risk, okay. But on the other hand, the deviation measure can be the risk of the difference between a random variable and its expected value. And under this, when would the risk measure be coherent? That exactly corresponds to the deviation measure satisfying this measure. All right, now we can see from this why the risk measure that had a safety margin cannot be coherent. Why it fails to have monotonicity in particular. It's because standard deviation does not satisfy that axiom. Standard deviation can exceed the difference between the top of the random variable. Now I want to say a little bit about getting more into the statistics side. So if we're going to use this uncertainty as some kind of probabilistic method, statistics are going to come in, and there's some obvious kind of connections between these subjects. For example, as I said, optimization, we may be dealing with statistics, and we'll have to use statistical analysis to understand it. But also in various estimation things, it comes down to optimization, because you're going to minimize some sort of error, for example, in regression, or different kinds of regression. If I get time, I'm going to discuss something about non-standard types of regression that are related to risk. So this is some sort of back and forth between the subjects. And let's get into this by looking at a kind of picture everybody has seen. Something having to do with a database from which we're trying to gain some information. So this is a very simple thing. I have 2 random variables, x and y. And I want to estimate the random variable y as ax plus b. I want to choose the coefficients a and b to be the best coefficients for this estimation. So this would mean that in this picture, I have a database that these pairs, I'm sorry that it's so poorly drawn, but I have pairs, x, k, y, k. I have a finite set of pairs. It's the accumulated data. And then I could put in here the y equal ax plus b line. And I'm trying to choose the a and b, so this line best represents the data. But best from what angle? So it's not a single way to look at it necessarily. But to move on with it, let's convert this temporarily, or alternatively, we look at it a different way. If I look at this z as the difference between the y, this would be the gap error between my estimated value and this y, and this is another random variable. but it's a random variable that depends on the choice of the parameters. So I want to choose the parameters so that I get the best random variable z somehow. All right, now in this picture, you can see basically it's just a trick where that line becomes the axis. So where we had things above and below the line, we now see them as above and below the axis. So where we had the yk, here we have the xk, we'll have the zk, which will depend on the choice of these random variables. Now, do you want them to be equally above or below or not? It's not clear. And then what measure do you want to apply to how close they should be or whatever? So this is where you get into generalized ideas of regression. So here's how to look at it from our general point of view. We have a random variable, some scalar, and we have some other ones, like factors in economics or finance. What is the current unemployment rate, exchange rate? We're trying to, with the euro, various factors that are random variables, and we want to be able to estimate this random variable y, like the price of IBM stock, from looking at certain other basic factors, because we're trying to get a simpler model. We want to have something that depends on a few variables. This will be useful in many ways. And so the idea is we're going to try to estimate y as some function little f of these other random variables. And the function should come out of some class. We can choose a class. So the most obvious classical case is to choose affine functions. So choosing an f is a choice of the little coefficients, C0, C1, up to Cn. And anyway, whatever the class is, then I will get this gap. The difference between the y and my estimate will be a gap in the random variable that will depend on the choice of f. All right, now the regression problem is to have some kind of error. What we choose here, gets interesting. Something about the size of this z. And we want to minimize that over all the choices they have available of this little function f. So the classical case is least squares. So I'm going to take the L2 norm of the sum of the squares, or the square root of it, which suits my fancy a little bit. So well, the idea of this is a measure of error now. This is going to quantify the non-zeroness in the random variable. But for instance, it doesn't have to be symmetric, like a norm. It could be something else. And you can have a lot of situations where your random variable some random variable that you're dealing with is supported by a database, and you're trying to get a formula for it by some sort of regression, but you only have a database. There's no analytical theory that gives equations of physics or chemistry to work with. So when you're going to do regression in that case, and you're interested in the consequences, the costs of your result from several angles, it could be, and we've demonstrated this in papers, you should choose the kind of measure of error to somehow correspond to the kind of risk you're going to do. Here, I'm going to skip over this, but it's an example that Yurasyev, my colleague, dealt with at the Boeing company. They were trying to do some materials for wings of airplanes, some composite materials, and well, in this particular case, we'll do some alloys. You're going to mix an alloy. You're going to take various metals and put them together and make a new kind of a metal. And then you want to test it, how strong it is, and so forth. And you could do many experiments, build it up, and then smash it and see how strong it was. And that would take $1 million, let's say. And then you try it again. And you can't have a very big database for what this is. And how are you going to do it? So it's going to come down to some sort of regression that maybe could cut short and save millions of dollars. So there are measures of errors. Should be convex, positive when the random variable isn't 0. You could, for example, take the expected value of some little error function. Now we're getting into something like fundamental statistics, which is coming into risk, because deviation measures are one of the basic things that I explained, and almost a one-to-one correspondence with risk measures. So suppose you take a measure of error. One idea would be squares, L2 norm, let's say. I take a random variable and I try to find the constant by this min. I try to find the constant C that is closest to this random variable with respect to my choice of the measure of error. If I took L2 norm, the answer would be the mean. The mean is the closest thing in the L2 norm. If I took the L1 norm, the answer would be the median. The various interpretations. So it's not just a single thing. Okay, and then the value that is closest, you could say that's the statistic, which is dictated by this particular choice of error. And then there's a sort of a meta theorem, which can be written more exactly than explained here, which says that if you do regression with such a measure of error, then that's the same. Remember, we're trying to find the function little f that so that that error is near to zero from some kind of. There's a way to say that it's the same as putting in the constraint that the statistic in question should be zero, and then subject to that, you're minimizing the deviation of your error. So, for example, at least squares, if I go back here for a minute, you see why this is an idea that really deserves a lot more research than it's gotten. If you did least squares, so here we have this picture. So it says we're going to introduce, by our choice of error, we're going to introduce that the zero level will correspond to a certain statistic. And then subject to that, we want to squeeze the error as close as possible around it with the corresponding deviation measure. So now if you're doing classical least squares, what that means is this becomes the average value of the error. And subject to that, you want the standard deviation to be as low as possible. But there's something called quantile regression. Quantile regression at, or say the 90th quantile, would be that you want, this is a 90th quantile line. 90% of the things should be below this, 10% of the things should be above, and subject to that, you're trying to squeeze it in a certain different way. But it's a huge subject. You could have many things, but it shows that if you are in a situation in risk, see, one of the problems in finance is they estimate everything by mean and variance, but all the risks are really in the tail of the distribution. And so the tail is not well taken into account by standard regression methods. Well, I already went through that. So I'm going to have to end very soon, but this is part of a sort of a picture is being built up in here. This is what we call the fundamental quadrangle of risk. And I started discussing measures of risk, and I showed how they corresponded essentially one-to-one with measures of deviation once you get to the right level of properties that you're assuming. So already there, the risk is some part of optimization, but you just saw now that the deviation measure is like a generalized statistics concept that can correspond to that, and it's coming from error. Now, I don't have time, and then there's a statistic that comes out, this S. I don't have time to discuss this exactly, but this is related to the formula for conditional value of risk and value of risk, and there's a way to generalize that, and there's a one-to-one correspondence about that. So somehow we come to the realization that it's really possible to work with optimization on a level of uncertainty without automatically being tied in to some different point of view of statistics than the traditional one. And that should somehow be exploited and expanded. And I have all these other things, but I'll just stop here and get to the various examples. And here are some references. And this is the paper that you could look at to see that overview of all those different things. Okay, I'll end there. Thank you.
Thanks, Larry.